No questions from chapter 16? I'm not going to be able to get your chapter 15 exam back until tomorrow, so I posted the key on Piazza. You can take a look at that if you want to go back and review some of the stuff. All right, so if there are no questions, we're going to continue with chapter 17.
Are we finishing chapter 17 lecture today?
We're going to continue. We still have a lot more to cover in chapter 17. All right, for chapter 17, did I talk about strong acid, strong base, K, very, very, very large, those things?
Yeah.
Okay. All right, now we're going to look at some other mixtures that we see. And so what other mixtures do we have? We have mixtures that are called common ion mixtures. A common ion would be something like this. If I take sodium chloride and HCl and mix them together, the common ion here is chloride. That would be one example. And so let's go ahead and do a problem like this. This would be more of a simple common ion, in which you just add everything up, all the species. And so here we start off with the biggest K, which would be sodium chloride. Sodium chloride is a soluble salt, so we know it should dissociate completely. And so let's put some values on this here. So if I had a beaker that was 0.100 molar sodium chloride and 0.100 molar HCl, and I want to figure out what is the inventory of this, then I would just follow the stepwise procedure, starting with sodium chloride. If I had initially 0.100 molar here, and 0 molar here, and 0 molar here, then where would that end up? Well, what is K for this? Very large. K is going to be very large. Soluble salts are strong electrolytes, so pretty much reacts to completion, or ionizes to completion in this case. So you end up with 0.100 and 0.100. Okay, then we go to the next biggest K. Maybe HCl was a bigger K, I'm not sure, but we could go in this direction. Well, HCl, will hydrolyze water to form hydronium and chloride. So here's where the common ion comes in, and that is, for HCl we're starting off with 0.100 molar, but the hydronium is going to be 0 molar. Chloride will be 0.100 molar here. And so we're starting off with some chloride to begin with. Normally if we have a pretty big concentration of chloride, do I expect the hydronium ion concentration to increase by much? No, normally I wouldn't expect, because you got a lot of product there. You got a lot of product there already. You need to generate as much to hit equilibrium. Normally not, but this is different because K is very large. When we have a very large K, it's pretty much a one-way reaction. And so even if I got a whole bunch of product there to begin with, it doesn't matter, because this is going to go to completion, liquid. And so this, we lose all of this, we form 0.100 molar here, and then we're going to form 0.200 molar here for the chloride. And so far I've generated 0.100 molar sodium. This chloride goes down here, and now I have 0.200 molar chloride. The only thing left is hydronium and hydroxide. So I go on to the next step here, which would be, how much additional hydronium am I going to get from Kw? So I go to H2O liquid plus H2O liquid. This is going to give me hydronium plus hydroxide. And so I'll take this hydronium, bring it over here. So the initial hydronium is going to be 0.100 molar. And the initial hydroxide, 0 molar. Change equilibrium. So at equilibrium, we're going to have 0.100 plus X molar and X molar here. And so I expect to generate some more hydronium and hydroxide in this step. Do I expect much additional hydronium here?
No.
No. In this case here, I don't expect much because we got a lot of hydronium, and so I can't expect much hydroxide generated. Whereas over here, it had no impact because of the difference in the K's. When you look at the K for this one, this is just Kw. Kw is 1.0 times 10 to the negative 14. And so that's going to equal the hydronium ion concentration times the hydroxide ion concentration, which is 0.100 plus X times X. Do you think the simplifying assumption should work well here? Yes. I think this is going to be about 0.100 X, and therefore X is 1.0 times 10 to the minus 13. If I look at the percent change is very small. 10 to the minus 13 over 10 to the minus 1 times 10 squared, very small. And so the simplifying assumption works pretty well. This is going to give me about 0.100 here, molar. And this is going to give me 1.0 times 10 to the negative 13 molar here. All right, so that's pretty much the solution inventory. So when I go back to this beaker, what are the species I'm going to find in solution? I'm going to find sodium ions. This is not ranked at 0.100 molar. I'm going to find chloride ions at 0.200 molar. Hydronium ions, just slightly above 0.100 molar. And hydroxide ions at 1.0 times 10 to the negative 13 molar. And so the reason I call this simple is it's just simple step by step. All the steps are additive in that sense here. So you can see the common ion, you just add the two values up. 0.100 from the sodium chloride plus the 0.100 from the HCl gives us a total of 0.200 molar common ion. But what about this common ion problem here? If I had a beaker that was labeled 0.100 molar HCl and at the same time 0.100 molar acetic acid, now I have a common ion problem again, but it's a little different this time. Because the common ion here is going to be H plus or hydronium. And so do I just simply add up the two? For example, here I have 0.100 molar H plus 0.100 molar H plus should give me 0.200 molar H plus. Can I just simply add those up? No. In this case, it doesn't work that way. And it's because of the K values. If you look at the K values here, the K value here is very large, the K value here is very large. We're going to supply that. Here, the K value is very large, so I expect 0.100 molar H plus here, but over here, I'm going to expect a lot less. Because for acetic acid, the K is only 1.8 times 10 to the minus 5. And so it's quite a bit smaller. So if I have these two acids in a beaker, what am I going to find as far as the inventory goes? Well, again, we'll just start with the largest K value here. The largest K value is going to be for HCl. So we'll have HCl plus H2O liquid. This is going to produce hydronium. And chloride. You should have the K value for this memorized. The K value is very large. Sometimes people don't have it memorized, and they come up and ask me, you didn't give me the K value for HCl. I need the K value to solve the ice table for X. I can't solve it. And then I tell them, there's enough information there. You should be able to solve it. In other words, you should have had it memorized. Because strong acids go to completion. Okay, so far we've generated 0.100 molar hydronium. Now we've got to think, because the common ion here is acetic acid, H+. And so let's go and figure out how much additional hydronium we're going to get from acetic acid. And so acetic acid plus water is going to give us hydronium plus acetate. The initial acetic acid is 0.100 molar. What's the initial hydronium? Yeah, 0.100 molar. Just carry it down. What's the initial acetate? 0. Now Ka8 is 1.8 times 10 to the minus 5, which means it's not so big. Because the change is definitely not going to be complete. So we're going to get minus X molar, plus X molar, plus X molar. And so at equilibrium, we expect 0.100 minus X molar, 0.100 plus X molar, and X molar. Yeah. Now, do I expect X to be very significant? No. Why?
You already have a lot of products.
Yeah, I already have a lot of product. I got 0.100. Yeah. If you compare it to the last problem, I already had a lot of product, the chloride, but I still expected X to be significant because K was very large. Here, K isn't so large. And so even though I have a lot of product here, with a large K, I could expect additional, but with a small K, I don't expect much additional. And so let's calculate it out. So Ka is going to be the hydronium times the acetate divided by the acetic acid. So that gives me 0.100 plus X times X divided by 0.100 minus X. You think the simplifying assumption should work well? I think it'll work great here because I have a lot of product. I don't expect much change. So this will be just equal to X. Let's calculate the percent change. Change is going to be 1.8 times 10 to the minus 5 divided by 0.100 times 100%. So this is 10 to the minus 1, 10 to the minus 4, 10 to the minus 2. 0.018%. So that was good. Simplifying assumption. So let's go ahead and calculate these. So the acetic acid will be 0.100 minus 0.40. 1, 2, 3, 4, 1, 8. So we need 3 more zeros here. 10 9 from 8, 9, 9, 9, 0. 0.099982 molar. Okay, 0.100 plus x, this is going to be 0.100 plus 0.1234018. 3 extra zeros there. It's sub 1800001. 0.100 sub 018 molar. Now, was much additional hydronium generated? Was a significant quantity? No. So if I was interested, let's say I wasn't interested in the inventory. Let's say I was interested in the pH of this solution. So I have a pH problem, and I have equal amounts of strong acid and weak acid. Take a look at where the hydronium comes from. Even though I started with equal amounts of strong acid and weak acid, the vast majority of the hydronium came from the strong acid, HCl, and a very tiny amount came from the acetic acid. And so this has a similar analogous problem in chapter 16. In chapter 16, if you're dealing with a weak polyprotic acid, most of the hydronium is generated in step 1. And typically very little hydronium is generated in step 2, 3, 4. And therefore, if you have a weak polyprotic acid and you want the pH, you just calculate step 1. Well, this is not a polyprotic acid. This is two different acids, but it is a polyprotic acid in one way, because step 1 we have this biggest K, and step 2 we have the next biggest K. And so in a sense, this is a polyprotic. It can be thought of that way. Sorry. So, in that sense, here, most of the hydronium will be generated by the strong acid. And so the simple rule here is that if you have a mixture of a strong acid and a weak acid, then the pH will be dictated by the strong acid. The only time that fails is if I do something like this. You know, what if I change the strong acid from 0.100 to 1.0 times 10 to the minus 9 molar? You know, if you have 1.0 times 10 to the minus 9 molar HCl, that's almost like pure water. Okay? And so if this is almost like pure water, then the pH should be dictated by the weak acid. But we'd still do the same steps. You know, we do step 1 here with the biggest K, and then figure out how much additional hydronium we get from step 2, which will be a lot more. And so in that case, we wouldn't do that. Well, anyway, this problem, we're looking for the inventory. To do the inventory, we have to do all the steps. And so I figured out this. Now, what should we do here? Should we go on to step 3, or should we double check this? We should double check these to make sure that these numbers here match K. Can you double check this? Does it check out? Yeah. Okay. All right, so that means we go on to step 3. And so what is step 3? Well, yeah, there's going to be one more hydronium ion contributor, and that's going to be water. But water should contribute a negligible amount of hydronium. Do you expect water to contribute much?
No.
Not at all, but water will contribute a significant quantity of hydroxide. And so the only reason we do this is to get the hydroxide. And so this ends up being hydronium plus hydroxide. And so we set up the ice table. Now Petrucci never sets up the ice table for this step, the final step. Do you know why? Petrucci doesn't set it up in the solutions manual because he does this. He automatically assumes the simplifying assumption and comes up with a simpler equation for this. So let me show you what I mean. And so the initial hydronium will be 0.100 sub 018 molar. The initial hydroxide will be 0 molar. And so this will be plus X molar plus X molar. Now, with a large quantity of hydronium present, the hydroxide can't build up so big. And therefore, the hydronium can't build up so big. So we're going to have 0.100 sub 018 plus X molar and X molar. And so Kw is equal to the hydronium times the hydroxide, which is equal to 0.100 018 plus X times X. Now Petrucci makes the simplifying assumption always. The simplifying assumption is going to assume that X is very small compared to this, which should be good because Kw is quite small, 1.0 times 10 to the negative 14. And so this is going to simplify to 1 from 100 sub 018 times X. And so this is usually how he has it set up. He just has a Kw is equal to this times X, ignoring the contribution of hydronium from Kw. That means X is equal to 9.9 times 10 to the negative 14. Give me one more digit.
9.8.
Okay, 9.998 times 10 to the negative 14. I want you to carry extra digits, because I need you to show me the round off step. Does that really impact this number at all? No, so this is going to be about the same point, just a little bit bigger, 0.100 sub 018 dot 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 molar. But this one it does impact. This is going to be 9.998 times 10 to the minus 14 molar. And so here we see a significant increase in hydroxide. Here we don't see a significant increase. So the final hydronium is going to be here. Well, if we calculate the pH, let's say the pH between the pH here is going to be 1.000. The pH here is going to be like 0.9999, which is going to round to 1.000. And so basically, whether we do step 1 or step 1 and 2, we're going to get the same pH. And for sure, step 3 is not going to really change the pH. But it does give us some hydroxide here, so we should include that as well over here. And that is, we're going to have, what are we going to have? We're going to have hydronium, 0.100 sub 018 dot 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 molar. We're going to have acetic acid, 0.099 sub 9 molar. Looks like, if we round this, it looks like acetic acid did nothing, right? If we round it, it goes back to 0.100. It looks like it didn't change at all. And then we have the acetate. What, 0.8 times 10 to the minus 5 molar. And then we have the hydroxide at 9.998 times 10 to the minus 13 molar. And that would be the inventory.
CL.
Oops, yeah, I forgot the Cl. The Cl minus would be 0.100. All right, so this was two different acids, but the method is very similar to what we've been doing all along, because what we've been doing all along has been the common ion. Step 1 generated hydronium, step 2 generated hydronium, step 3 or hydroxide. And so we've been doing this all along. Okay, let's take a look at a different type of mixture now. In this mixture, you're kind of thinking common ion, but maybe not so much. And so an example of this would be something like HCN of hydrocyanic acid with ammonia. Hydrocyanic acid with ammonia produces what?
NH4 and Cn minus?
Yeah. And so we get NH4 plus and Cn minus. What do you think K for this is? Well, what we have is we have a weak acid and a weak base. Yeah, it's going to be small. Only when we have a strong species will it be big. And so K is going to be small. So what do we do about the inventory and or pH? Well, if K is small, what does that tell you? It tells us we're going to have an equilibrium mixture. That is, what we're going to have is we're going to have these species coexist in some ratio. In fact, if it's small, we're going to have mostly reactants unreacted, right? And so even though this is an acid-base neutralization, it doesn't completely neutralize each other out. And so if we look at these, this is an acid, this is a base. And so what we have is we have this acid and base coexist in the same solution. When we have an acid and base coexist like this in significant quantities, we call it a buffer solution. The reason we call it a buffer solution is if you have a beaker of this stuff, we're going to have quite a bit of HCN unreacted and quite a bit of ammonia unreacted. And so you have both an acid and a base. Now, if you were to add strong acid to this, like HCl, if you add strong acid to this, the ammonia would neutralize that or attack it. And so what happens is adding strong acid to this solution, it gets neutralized, but likewise, adding a strong base to this solution, the HCN attacks it and neutralizes it. And so this solution is capable of neutralizing both strong acids and strong bases, therefore it's called a buffer solution. Well, how do we figure out what the pH of this buffer solution is and what the inventory is? What do we do? Well, I'll tell you what we know. We could do Ka of HCN, we could do Kb of ammonia, we could do Ka of ammonium, and Kb of cyanide. We have a whole bunch of equilibria there. And those equilibria are going to be tied together by, like for example, the Ka equilibria generate hydronium, the Kb equilibria generate hydroxide. And what ends up happening here is we have to do these simultaneously. And so it's not just a simple stoichiometry problem where we get the acid neutralizing the base neutralizing the acid. It's more involved. And so this is simultaneous beyond M1B. So a simple problem, but we aren't going to really solve it. So let's call this the buffer 1, type 1. Now I'm going to go to buffer 2. A buffer type 2 would be something like sodium bicarbonate, AQ. If I have sodium bicarbonate, AQ, then we know something about bicarbonate. Bicarbonate is an acid, and bicarbonate is a base, right? Because bicarbonate is amphoteric. And so if you have bicarbonate, if you add strong acid to this, the strong acid would be neutralized by bicarbonate because bicarbonate is a proton acceptor. Or if you add strong base to this, so the strong base would be neutralized because bicarbonate is a proton donor. It can go either way. And so let's say I just have bicarbonate in solution. What is the pH of this solution? What is the inventory of this solution? So why don't you try to figure out what you're going to do about the pH? Because let's say this, bicarbonate can collide with water, like an acid, to generate hydronium and carbonate. Ka for bicarbonate, we'll just use the one on the book, on the chart here, 5.6 times 10 to the minus 11. But bicarbonate can also collide with water to generate hydroxide, from carbonic acid plus hydroxide. The Kb for this is equal to Kw divided by Ka for what acid? Ka for bicarbonate or Ka for carbonic acid? And so using the chart value there, there's 1.0 times 10 to the minus 14 divided by the Ka for carbonic acid, which is 4.3 times 10 to the minus. Can someone read that? 4.3 times 10 to the minus 7, is that right? Yeah, 4.3 times 10 to the minus 7. Okay, so this gives us what? Times 10 to the negative 8. All right, now Can you go ahead and do this for me? Can you figure out what the inventory and or the pH is for bicarbonate? I'm going to just make a 0.100 molar. Let's see. Sodium carbonate, bicarbonate solution.
Sodium bicarb.
0.100 molar sodium bicarbonate. Now, what is the pH and what is the inventory of this? Okay. And so why don't you go ahead and give that a shot right now. I'll let you work on that. Let me stop there.